So this morning, hello everybody. I'm going to be working on a worksheet from a 2T I have, and take a look at this and see what I think is the best way to answer these questions. Again, when you're dealing with students that you're tutoring, you never know what their professor is going to give them. So sometimes it takes time to understand their professors, and in this case, some of the questions, the way they're worded, are very different. And some of the confidence intervals that are asked for here are kind of odd because normally we wouldn't ask for a 91%, 93%, 98%, but you could. So it's a good way to test how much somebody knows about confidence intervals. But just before I go on, I ask that you please subscribe to my channel. And it helps me produce videos like this. It takes a lot of effort and a lot of work for me to do these. So I appreciate it if you subscribe. It doesn't cost you anything to subscribe, but it helps me out. If you like my content, I appreciate it. Also like this video. Yeah, watch it through. All right, so here's the first item. So I worked these out by hand, and there are some areas where I disagree with stuff. So we'll have to talk about that. Okay. So here's the question. Find the critical value, the z-value that corresponds to a 95% confidence interval. So all confidence intervals are some estimate plus or minus a margin of error, right? Plus or minus a margin of error. See, I don't know if I wrote down the confidence interval equation here. I don't believe I did, but so what I mean by a margin of error is a margin of, well, maybe I did. Let me see, hold on. Let me see, maybe in the second one I did. Yeah, here it is actually. So you have an estimate of some sort, and then you have a margin of error. Now, this is dealing with proportions, which we'll get to in a moment, but you always have a margin of error, right? So the margin of error is going to be some critical value. And in this case, we're assuming normality. So we're using a normal distribution and we're using z-values. Those are standard deviations away from the mean. A z-value is a standard deviation away from a mean. So it's a value that's been transformed so that we can have everything in standard deviation terms. The question here was a 91% confidence interval. It's kind of like I said, it's an odd one. So how do I approach this? Well, first thing I have to do is I have to find where the cutoffs are, right? Where the cutoffs are for this 91% confidence interval. If we subtract this from 1, so the confidence interval is the interval, well, in this case, confidence interval is the interval in which we believe the true population value resides. So if we look at this distribution here, it's going to be, we're 91% confident that the true population value is between somewhere and somewhere, right? Between these two different points, right? So that's the interval, right? So that due to symmetry, because this distribution is symmetrical, it's going to be equally spaced from the population mean to the left and to the right. So the complement of confidence is alpha. That's basically being non-confident, or the probability of a false positive result. That's by definition, what alpha is. So 1.1 minus 0.91 is 0.009. Because we're doing a confidence interval and the interval surrounds our estimate, we have to split this alpha in two. Half of it's going to go be at the top of this distribution with a positive end. And these go to asymptotes go to infinity, right? These tails go to infinity, and half will be underneath that. So this is basically where my cutoff point is going to be, right? So I need to find my cutoff point, whatever this value is that initiates the top 4.5% of the distribution, and then the cutoff here that exceeds the lower 4.5% of the distribution. Now, when I'm just trying to find that point, I need everything to the left of whatever this point is, right? I need everything to the left. So what I do is I take that 0.91 and I add the lower 4.5% to it, right? Because what I have from here with the 95% refers to is starting here and ending here. But when I talk about this cutoff point, it's got to include everything below below it, and that includes also the lower 4.5%. So I take the 91% and add 4.5, I get 0.955, right? And all right, so I got 0.955. What I'll do is I'll go into my table here and look for 0.955. So this is a classical Z table. There's different kinds. And in this Z table, you have everything to the left. There are also Z tables that only work with half of the distribution. And in my textbook, I use half of the distribution. But in this case, we look for, and this is the area under the curve. And this area under the curve we're looking for represents 95.5% of this whole distribution. So the values here in the meat of this table are the area. So I look for 0.955. And it's going to be 1.7, well, 0.9554. That's pretty close, right? There's 0.9545 and there's 0.9554. So I'll just go with this one. It's 1.7. And the way you read this, this is to the hundredths place. This is to the tenths. So this would be 1.70. This would be 1.71 and so on. So we use the 1.70, 0.9554. Right, so 1.70 is my critical value, and it's the answer to this problem. Right? And it should be, so if I go to the worksheet here, let me just show you this worksheet. So this worksheet says the answer is 1.70. It really technically should be either plus or minus 1.70, or you could say the absolute value of 1.7, because it's going to be plus or minus, right? So it's on both sides, right? It's on both sides of the distribution. So you'll see in my answer, I would put either absolute value or plus or minus 1.7. Second question is for a 93% confidence interval. What are the critical values? So we're following the same process. Do 1 minus 0.93 is 0.07. We cut that in half, just like we did before. And so it's 0.035. Take 0.93 again. The 0.93 represents this area now. Instead of 0.91, it's 0.93. Right? So we do 0.93 subtracted from 1, we get 0.07. Divide that by 2 is 0.035. 0.93 plus 0.035 gives us everything to the left of whatever that cutoff point is. We get 0.965. That's my area under the curve to the left of that point. So I'm going to go back to my table. 0.965. See, I already forgot, but it's right somewhere like right here. Wait, did I say 0.965? What did I say? Uh, I said, yeah, 0.965, 0.965. So when you get old, you start forgetting stuff. 0.965 is right here. This is the closest one right here. So 1.80, 1.81. So the answer would be plus or minus 1.81. Or absolute value of 1.81. For the third one, the 98% confidence interval. So this gets easier as you go on, right? If this were an exam, you'd hope you get a lot of these because it gets easier and easier. So it's 1.1 minus 0.98 equals 0.02. Divide that sucker by 2, you get 0.01. 0.98 plus 0.01 is 0.99. So the approximate answer there is 2.33. Again, we look for 0.99 in that table. 0.99, 0.99. 0.99, where's 0.99? So it's like right here. 0.99, so 2.3 something. 2.3012, 0123, 2.33, is that what I said? Yeah, about 2.33. Okay. Again, so that's absolute value. And I put this symbol here, all these symbols mean approximate because again, I'm using a table and I can't be perfect in the table. Okay, this next one is interesting. And here I differ with the way this professor did it. Now, I can understand why she did it this way. That's fine, but it's not correct. Okay, so assume that a sample is used to estimate a population proportion. Find the margin of error, E, that corresponds to a given statistics to the to the given statistics and confidence level, round the margin of error to 4 decimal places. So this question wasn't written really well because you're wondering, well, what does x equal 50 means, right? So this is some kind of a number of successes because when we're dealing with proportions, so this is actually a normal approximation of a binomial. So more information should be given. So I say, oh, okay, this is a normal approximation of binomial. So that means there's 50 successes, right? So, but it just says here x equals 50. When I first saw this question, I'm like, what? Okay, so upon sitting around a bit, I figured it out. Okay, so they want the 95% confidence interval. Is that what it said? Margin error, blah, 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 assumed sample, or they want the margin of error. Okay, find the margin of error. Okay, so we know right away that the critical value for a 95% confidence interval, and you should know this one. This should be memorized. It's 1.96. So that's going to be 1.96. And you can go through the process of looking it up in the table or wherever. We know that our n or sample size is 380, and we're looking at 50 successes. So there's certain things that we need here. Now, I mentioned that I think the way it was done wasn't correct. It wasn't correct. So there are two different equations that you can use to calculate a margin of error, and both of them have their own issues. This is I think hold on, the walled confidence interval. Let me go back here. Give me a second. It's called the walled, right? Not where's Waldo, but the walled confidence interval. Yes, right here. Yeah, walled confidence interval. And it has some issues because you can, so in fact, it says, so researchers comparing different confidence interval equations for proportions found that the method to have flaws, including having limit values that fall outside of 0 and 1, which are not possible values for proportions, right? So that's a problem. By the way, this is my textbook. Sometimes I just forget stuff that I wrote. So what we do instead is we use this better estimate for the confidence interval. Okay, but this isn't what was done. What this instructor did was she used this standard deviation, right, as her standard error. So we use standard errors when we're comparing samples to populations because samples aren't a single unit. Samples have a number of individuals, and we have to adjust for the number of individuals in the sample, right? And this doesn't do that. So this is just a standard deviation. So I'll show you what this instructor did here. So first of all, I just did these on my own using the correct equations. So with the walled confidence interval, I got 0.0788. And then with this Wilson method, I got 0.17. What, no, is that it? Yeah. 0.0174. And then I used this instructor's method. So I had to kind of figure it out. I said, what was she doing? So I played around a little bit and I realized, oh, okay, so she's using the standard deviation as her estimate of the standard error. Okay, so then I got it. So let's start by calculating the proportion. Well, the x was 50 again, so that's what she meant, was 50 successes divided by 380. So that gives me 0.132. So for this equation that she's using here for the standard deviation, it's the estimated proportion times 1. So the little hat means estimate times 1 minus p estimate divided by n. So it's the square root of all that times whatever the z value is. So I'm sorry I did this backwards. There's arrows everywhere. It's because I was trying to figure out what she was doing. So we have our estimate of 50 divided by 380 is 0.132. We have its complement is 0.868 because 1 minus 0.132 is 0.868. So her standard error then would be P. Sometimes we say instead of 1 minus P, we say Q. So I could say P times Q is 0.132 times 0.868 divided by 380. Take the square root of that, right? So I get my standard, that's the standard error. And to get the margin of error is this z value times the standard error. So I multiply 1.96 times 0.1736 and I get 0.0340. 0.0340. So that's the correct answer. And we go to her worksheet. We find that it's right here. So it'd be B. All right, the next one is a random sample. So okay, now I know what this professor wants. Mind you, though, that if you were in my class, you'd get that wrong. Okay, but it's okay. One of the things about being a good student in a specific class is adapting to your professor. Being a good student universally is using the right technique, but that's a whole different issue. No time to deal with that right now. In a random sample of 192 college students, 129 had part-time jobs. Okay, so now we can easily calculate the proportion. So we're probably thinking 129 out of 192. Again, this question isn't written very well because shouldn't it say what is the proportion? Identify the proportion of individuals having part-time jobs and then find the margin of error. It should have added something here, but it just says find the margin of error for the 95% confidence interval used to estimate the population proportion. All right, let's go ahead and do that one. So now that we know what we need, I don't need to worry about anything else anymore. So here's my margin of error equation. N is 192, N is the sample size. You got X is equal to 129. So that's the number of successes or people having part-time jobs in this case. 129 divided by 192 is 0.672. The reciprocal of that, or the if you want to call it the complement of that, is 1 minus 0.672 or 0.328. So notice here I wrote standard deviation as the standard error. There are times when you do use the standard deviation as the standard error. Like there's some method that I use for doing intra-rate or reliability. In that case, it's okay because I'm doing one person, right? But when we're using a sample from a population, we really want to use the true standard error. But here we're using standard deviation as an estimate of the standard error. So we have P times 1 minus P over N. Again, the hats mean estimates. So 0.672 times 0.328 divided by 192, take the square root, and we get 0.0339. That's funny. Like your warning, warning, warning. The margin of error is 1.96 times 0.03 distribute dot 0.0339 or 0.0664. So we look for that answer, 0.0664, 0.0, there it is. So I don't know what would happen to me if I took that course. If I was me just as I am now. The funny thing about this is that as a tutor, sometimes you have to be very confident in yourself because if you give the answer and then you see it's not equal to the professor, a lot of people assume, well, the professor's right. How could the professor be wrong? And you could like doubt yourself. But thankfully, in these cases, I have my own textbook, and so I can say, wait a minute, what the heck did that person do? All right, 98% confidence interval. 98% confidence, the sample size 800, blah, 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 blah. All right. All right, so let's go here. At 800, P is 40%. So this is better. So it's telling me what the proportion is, telling me what N is and what this oddball value would be here. So I know my estimated proportion is 0.4. 1 minus 0.4 is 0.6. See item 3, because we calculated this earlier. That's why I said see item 3. So go up to item 3, right? So we calculated a 98% confidence interval before, I mean, the Z value for a 98% confidence interval. Did I do that right? Yes, she wanted 98%. Okay. So we did that before, so I could just plug that value in, right? right? 2.33 times the square root of p times 1 minus p over 800. Get 0.0404. And let's check, see if that's right. Obviously, I know it's right because I already checked it. Yeah, here it is. All right, so that's those. So those are again, so that's I had to figure this out on my own. Use the given degree of confidence and sample data to construct a confidence interval for the population proportion using a calculator command. I don't have that calculator, so I'll just do this on my own. So we know n is equal to 56, x is equal to 30, and here's the confidence. So basically we're doing the same thing we did before. So we need the margin of error so we can construct the confidence interval. That's basically what we're doing here. And I think this is the first one, right? Yes. So we had 30 of 56, so our proportion of successes is 0.54, or failures, if you will. 1 minus success is 0.46. We use success in probability or proportions. Well, probability, in this case, are the same thing. The estimated probability. The 95% confidence interval would be the estimated proportion plus or minus whatever the z value is here times this standard deviation that she's using. And then you follow the same procedure as before. You always add and subtract the standard error from the estimate. So this is called a point estimate, and what we get here is an interval estimate. So the standard error is 0.13, so I get 0.54 minus 0.13 is 0.41, and I get 0.54 plus 0.13. That's what the plus or minus means. It's 0.67. I think there's one where I might have differed a little bit because of rounding that she did. I said answers A because she did 0.405 and 0.667. And what did I get? Yeah, 0.405, so 0.1. So I just rounded up. Okay. So I did 2 decimal. Usually I do 3 decimal places, so I must have been lazy at this moment. Number 8, for an 88% confidence interval. So let's read the question here. Number 8, n is 109, x is 65. You have 88% confidence. All right. You want an 88% again, so your successes is 65 out of 109. So that's how we're going to get our proportion. All right. So we have 65 divided by 109, or 0.596. 1 minus p is 0.404, right? 1 minus 0.596 is 0.404. Our 88% confidence interval is, our point estimate is 0.596 plus or minus. So we needed a z value associated with 88%. So you can look up how we just did that in the beginning. We did these different estimates. So you should by now go back and look at that if you don't know how. But it's 1.55. That's our z value here, times p times 1 minus p. Excuse me, times the square root of p times 1 minus p over 109. And I get 0.523 to 0.669. 523 to 0.669. 523 to 0.669. Here it is. D is the answer. Now these ones I did, but then I had completely different answers from her. So here's the problem with this question. The problem with this question is that while I know what the margin of error is, but when we're doing an estimation of a sample size, we're going to say, well, what's the sample size we need to detect well, in this case, it's 0.5% difference, right? So that's a prototypical question. We need our alpha, right? Our alpha is 0.04, so we can find our z value, right? It says P and Q are unknown. So P and 1 minus P are unknown. When they're unknown, you usually will put in 0.5, and that's pretty typical. So what we're looking at is our the value that we really want is 0.505, right? Because this is the estimated proportion, and this is what we're looking for. But one thing that we're missing here, or other information that we're missing here, is we also need what our power estimate is. Because when we're doing sample size, we need to know, well, what's our estimated power? Generally, it's zero point 0.8. I did these calculations and I did not get 42,000. I did. So what I used was, in my book, I talk about calculating sample size. Yes, here I derive the equation for calculating sample sizes, starting with the power, right? 1 minus beta. Beta is the probability of a type 2 error, which is the complement of power. So I derive this equation for calculating the sample size. So I did this and I was getting smaller values. So I'm not really sure what she was doing, and I couldn't just figure it out. But you can certainly look at my equations, which are correct. Um, so I'm not 100% sure what she wanted there. And then a couple of these are just like, they're just interesting. Margin of error is 0.07, confidence is level 0.95, prior study. So here she gives you an estimate of the P. So then what you're looking for is 7% increase from that. So instead of 92%, you're looking for 99%. So you're looking at what's the sample size required to detect a margin of error of 0.07. And again, we have no information on the power and other stuff like that. So these are just some interesting questions. I'd like to see what the instructor did there. And the rest of these are just some variations of what we already did. All right. So I hope this is helpful to anybody watching. Thank you very much.